Welcome to the problem solving session number 1 of the polymer reaction engineering. Now, previously we have studied about the quantitative analysis of series reactions in plug flow reactor and a batch reactor. We discussed about the quantitative treatment of mixed flow reactor, first order followed by the zeroth order reactor and a zeroth order followed by the first order reaction. Now here this particular lecture we are going to solve some typical numerical problems. So let us start with the first problem. Here a liquid A decomposes by second order kinetics, and in a batch reactor 50% of A is converted in 5 minutes run. So the thing is that how much longer would it take to reach 75% conversion. Now for the second order disappearance, let us start with that. The second order disappearance of a reactant A. Now rate can be written as minus Ra is equal to Kca square, that is equal to dCA upon dt, or minus dCA upon dt is equal to Kca square. Now on rearranging and integrating, we have Ca naught Ca dCA upon Ca square is equal to 0 to T K dt. This can be written as minus Ca upon minus 2 plus 1 minus 2 plus 1 Ca naught Ca, this is equal to Kt. This can implies to 1 upon Ca minus 1 upon Ca naught, this is equal to Kt, or 1 upon Ca naught, Ca minus 1 upon Ca naught, this is equal to Kt. So in terms of conversion, minus 1 upon Ca naught plus 1 upon Ca naught 1 minus Xa, this is equal to Kt, and this is equal to 1 upon Ca naught into minus 1 plus 1 upon 1 minus Xa, this is equal to Kt, and 1 upon Ca naught into Xa upon 1 minus Xa, this is equal to Kt, or T is equal to 1 upon K Ca naught Xa upon 1 minus Xa. So now for 50% conversion, T50 is equal to 1 upon Kca naught 0.5 upon 1 minus 0.5, and T50 is equal to 5 minute, that is equal to 1 upon Kca naught. So when we sort about the time required for 75%, so it can be represented as T75 is equal to 1 upon Kca naught 0.75 upon 1 minus 0.75, and T75 is equal to 5 into 0.75 upon 2.25, that is equal to 15 minute. So here 10 minute extra, you see that here 10 minute extra would be required for 75% conversion of reactant A. So this is the answer. Now let us take the second problem. Now this problem says that if a gaseous feed is given, these are the following coordinates, like Ca naught is equal to 200, Cb naught is equal to 100 and Ca is equal to 50. For the reaction A plus B is equal to R, then you need to find out the values of Xa, Xb and Cb. So you see that we are having this particular reaction. Now in an isothermal single phase flow reactor, let us assume that this is an isothermal single phase flow reactor that is operating at under the constant pressure. So if reaction is proceed in PFR, so in that case you are having this symbolic representation. So at T is equal to 0, Ca naught is equal to 200, Cb naught is equal to 100 and Ca is equal to 50. So let initially 300 moles of reactant reactant, that is feed gas to the reactor, then Xa is equal to 0, T is equal to 0, that is no product are being formed. So V is equal to 200A plus 100B plus 0, that is equal to 300. Now at Xa is equal to 1, so you can represent V is equal to 0A plus B plus 200R, and that is equal to 100. So epsilon A can be written as Vxa is at 1 minus Vxa equal to 0 upon Vxa equal to 0. So in that case epsilon A, that is equal to 100 minus 300 upon 300, that is equal to minus 2 upon 3. Now similarly for B, now at Xb is equal to 0, V is equal to 300, now Xb is equal to 1, V is equal to 100A plus 0B plus 100R, and that is 200. So when we write about the epsilon B, that is 200 minus 300 upon 300, that is equal to minus 1 upon 3. Now here we needless not to mention that Vxb is equal to 1 minus Vb at 0 point, then Vxb at 0. So Xa is equal to Ca naught minus Ca upon Ca naught minus epsilon A Ca, or we can write Xa is equal to 200 minus 50 upon 200 plus minus 2 upon 3 into 50, and that comes out to be 0.9. Similarly, Xb is equal to B Ca naught Xa upon Acb naught, and that is 1 into 200 into 0.9 upon 1 into 100, that is Ca naught Xa upon A is equal to Cb naught Xb upon B, where A is equal to B is equal to 1, as the stoichiometric coefficient of A and B are 1. So in that case Xb is equal to 1.8, and which is not at all possible. So this is the answer to this one. Now let us take the problem number 3. Here we have given a gaseous feed which is maintained at T naught is equal to 400 and initial pressure is 4 atmosphere and initial concentration of A is 100 and the initial concentration of B is 200. They enter into the vessel and you need to find out the temperature and the pressure. Now here the reaction is given as A plus B is equal to 2R and temperature is 300 Kelvin and final pressure is 3 atmosphere and Ca is 20. Then you need to find out the XA, XB and CB. So again we see that this is my reactor where we are performing A plus B to R. Now the initial condition that is maintained at Ca naught is equal to 100, Cb naught is equal to 200, T naught is equal to 400 Kelvin and P naught is that is pressure, initial pressure is 4 atmosphere. Now the final thing that is Ca is equal to 20, T is 300 Kelvin and P is 3 atmosphere. Since the above system is a gas and change in moles are negligible, therefore epsilon A is equal to 0 and epsilon B would also be 0. So for varying temperature and pressure for varying density, we know that Xa is equal to 1 minus Ca upon Ca naught T P naught upon T naught P divided by 1 plus epsilon A Ca upon Ca naught T P naught T naught P. Now this comes out to be 1 minus 20 upon 100 into 300 into 4 upon 400 into 3 divided by 1 plus 0 and that is 0.8. Now for XB we know Ca naught Xa upon A is equal to Cb naught Xb upon B, where Xb is equal to B Ca naught Xa upon A Cb naught, where A and B both are the stoichiometric coefficient, that is small a and small b, they are the stoichiometric coefficient of the reactant, and again the reference reaction is A plus B is 2R. So A is equal to B is equal to 1, that is the stoichiometric number. So if we substitute the things in this particular equation Ca naught Xa upon A Cb naught, then Xb will become 1 into 100 into 0.8 upon 1 into 200, that is equal to 0.04. So if for Cb we can write Cb is equal to Cb naught minus Ca naught Xa, and this is 200 minus 100 into 0.8 and Cb comes out to be 120. That is my desired answer. Right. So let's take another example, that is problem number 4. Now here if a given reaction, that is the reaction is given to you, that is A is converting into B. Now this particular reaction is to be carried out isothermally in a continuous flow reactor. You need to calculate both the CSTR and PFR reactor volume necessary to consume 99% of A when entering molar rate is 2.5 moles per hour. You may assume that the reaction rate minus Ra is given with this one, and the entering volumetric flow rate is 10 decimeter cube per hour. Now here we have given A is converted into B. Now initial things are 10, volumetric flow rate is 10 decimeter cube per hour, Ca is equal to 1 minus 0.99 because this is the 99% conversion, Ca naught, and Ca is equal to 0.01 Ca naught. So entering molar rate Fa naught, that is equal to 2.5 mole per hour. Now Fa is equal to Ca V naught and Fa naught is equal to Ca V naught, and we can write Ca naught is equal to Fa naught V naught, that is equal to 2.5 mole per hour divided by 10 hour, and that comes out to be 0.25 mole per decimeter cube. Now let's take the gradual example, like for CSTR, the general mole balance equation is V is equal to Fa naught minus Fa upon minus Ra, or V is equal to Ca naught V naught minus Ca V naught upon minus Ra, or it can be represented as V is equal to Ca naught V naught minus Ca V naught upon K, and that is 0.25 into 10 minus 0.01 into 0.25 into 10 upon 0.5. So this V comes out to be 49.5 decimeter cube. Now this is the required volume for CSTR to consume 99% of A. Now if we talk about the PFR, for PFR the general equation for PFR, that is d upon dV is equal to minus Ra. Now if we can write Fa is equal to Ca V naught, or Fa naught is equal to Ca naught V naught, that is the constant volumetric flow rate, V is equal to V naught. Now here d Ca V naught upon dV, that is equal to K. Now if we integrate both the side, we may have V naught upon K, Ca naught to Ca dCa, that is equal to 0 to V dV, and that comes out to be V naught over K Ca minus Ca naught, and that is equal to V. So V is equal to minus 10 upon 0.05 into 0.01 minus 1 into 0.25, and V comes out to be 49.5 decimeter cube. So the volume required for CSTR and PFR is same due to the rate constant K is independent of the concentration term. So by this way you can evaluate both the things. Now let us take another problem, that is for an elementary reaction A plus B equal to P, the reaction rate is given at 500 Kelvin is 10 times that at 400 Kelvin. So you need to calculate the activation energy for this particular reaction. So here you can have A plus B, we can utilize this reaction A plus B P. So the rate equation for this elementary reaction can be minus Ra is equal to K Ca Cb, that is equation number 1. Now if here K is the rate constant. Now if we write in terms of the Arrhenius law, then it can be represented K is equal to K naught e to the power minus E upon RT, because it is the need of the problem. Now from equation 1 and 2 we can write minus Ra is equal to K naught e to the power minus e upon RT Ca Cb. That is the equation number 3. Now according to the question, if the reaction rate at 500 Kelvin is 10 times that for 400 Kelvin, so minus Ra1 is equal to K naught Ca Cb e to the power minus e upon RT1. Now let T1 is equal to 500 Kelvin and T2 is equal to 400 Kelvin, and minus Ra2 is equal to K naught Ca Cb e to the power minus e upon RT2. So if we write this minus Ra1 upon minus Ra2, that is K naught Ca Cb e to the power minus e upon RT1 upon K naught Ca Cb e to the power minus e upon RT2 is equal to 10. This is given. So minus Ra1 upon minus Ra2, that is equal to e to the power minus e upon r into 1 upon T1 minus 1 upon T2, that is equal to 10. And that is why e upon r into 1 upon T2 minus 1 upon T1, that is ln 10, or e upon r into T1 minus T2 upon T1 T2, that is ln 10. Now E is equal to ln 10 into R into T1 T2 upon T1 minus T2. Now if we substitute all the values, that T1 is given, T1 is 500 and T2 is 400, and ln 10, then, and if we substitute the value of R is equal to 8.314 with units, then E is comes out to be 38.2874 into 10 to the power 3 joule per mole. That is my answer. Now let us take another example, that is problem number 6, that reactant A decomposes in a batch reactor by zero order kinetics. Now if initial concentration of A is 1 kilomole per meter cube and for a reaction time of say 1000 seconds, the conversion is 50%. Now you may assume the isothermal condition, then you need to find out the rate constant for this particular reaction which is given, and what will be the conversion for a reaction time of 3600 second. Now see, as per the problem, the reactant A decomposes into the product by zero order kinetics. So the rate equation can be given as with respect to the A, minus Ra is equal to K Ca naught, and that is equal to minus Ra is equal to K minus dCA upon dt, and minus dCA is equal to K dt. So if we integrate both the side from time t is equal to 0 to time t is equal to t, then it can become minus Ca naught to Ca dCA, that is equal to K 0 to t dt. Now if we go ahead with this one, then this may become minus Ca naught Ca equal to K t 0 to t, or minus Ca plus Ca naught, this is equal to Kt, and finally we can write this Ca naught minus Ca is equal to Kt. That is my equation number 1 for this problem. Now as we know that for conversion, Ca is equal to Ca naught 1 minus Xa. Now this can be Xa is equal to Ca naught minus Ca upon Ca naught, that is equal to Ca naught minus Ca, that equal to Ca naught Xa. That is my equation number 2. Now see, from these two equations we may have Ca naught Xa is equal to Kt. So the when we are talking about the reaction rate constant, then K is equal to Ca naught Xa upon T. So K is equal to 1 into 0.5 upon 1000, that is kilomole per meter cube second. So we can write K like this. Now let us talk about the second part, that is conversion for T is equal to 3600 second. Now Xa is equal to Kt upon Ca naught, that is equal to 1 into 0.5 divided by 1000 into 3600, that is Xa is equal to 1.8, that is more than 1, which is not possible. So the time required for 100% conversion, T is equal to Ca naught Xa upon K, that is equal to 1 into 1 into 1000 upon 0.5 into 1, and T is equal to 2000 second. So that is all of the reactant A will be consumed or convert into the product after 2000 second. So conversion after 3600 would be 100%, and that is my answer. So in this particular lecture, we discussed the various problems related to the plug flow reactor and the CSTR. And again, for the theoretical part, you may refer to the lectures as well as the references given in this particular slide. Thank you very much.